Hello everyone, my name is Aadarsh. I'm from Seattle, Washington, and presenting about the development of my project, Machine Learning Powered Assistive Glasses for the Visually Impaired. So 200 million people around the world suffer from visual impairments every day, and this takes a toll on their navigation, their independence, and just their everyday life. Visual impairments are defined as any kind of vision loss that affects a user's ability to perform everyday tasks. So there is current technology that is trying to solve this problem, and the most common one right now is the white cane. And a white cane, if you're not sure what it is a 4-meter long stick that essentially is waved in front as you walk about your day, and then it will hit objects before you get to them so that you're aware that they exist and you can take whatever steps needed to avoid them. The problem with this is, while it has proven to work successfully, it cannot really give a lot of detail back to an individual. So all I can really tell is an object's distance from me, or an object, maybe its shape, and sometimes its texture. There have been some improvements to the white cane with a device called the ultra cane. The ultra cane essentially uses ultrasonic sensors and a haptic feedback to communicate back to the user of its surroundings. However, visually impaired users have reviewed this device and said that the ultrasonic sensors are incredibly inaccurate, and haptic feedback has been proven to be incredibly hard to understand and really doesn't provide any useful information. Another recent development is the Meta AI glasses, which use computer vision to act as like an AI assistant to a user. So anyone can wear them and go about their day. It'll analyze the surroundings, you can ask it questions, it'll tell you what it sees, and all of that. The problem is these glasses were designed to help people that are already visually able. So the kind of responses you get assume that you can already see your surroundings. So if a visually impaired person were to try and use them, they won't get any information that would actually help them navigate through an area. So my solution is to utilize that same machine learning technology, but then tailor it and train it to be specific for the visually impaired people, to give them a clear understanding of their surroundings and help them navigate an area. So after researching on visually impaired people's needs and their struggles, I narrowed the engineering goals for this project down to 3 things: accuracy, range, and convenience. For accuracy, I wanted to be able to have precise, detailed descriptions of a user's surroundings. So this would include everything about the scenery. It could be object distance, range, size, texture, color, everything that they would need to know. Next, it should be able to detect things from much farther out than just 4 meters, like an ultra cane or a white cane, so that users can be warned much earlier of risks. And finally, convenience. It should be completely self-sufficient. There shouldn't have to be any adjustments from a user, and it should be able to work on its own. So with all these things in mind, I developed Iris, and this is what it looks like. The system pipeline is split into 3 stages. There's input prompts, the large language model processing, and the output prompts. So I'll start with the large language model processing, because that's where the bulk of it is. Inside the processing is the machine learning architecture, and inside of that, more specifically, are neural networks. Neural networks are designed based on the human brain, like the way we think, and it looks something like this. There are input neurons, which go into multiple layers called hidden layers. All of these are neurons, and all of that comes out into an output neuron. So every neuron in this diagram is connected to the next one in the layer, so that after the output from one neuron can activate the relevant neurons in the next layer, and so forth until it comes to just one output. So let's take this image of a cat, for example. We can tell it's a cat because of key features such as its shape, its texture, its color, and especially the facial features. But this is how a computer will look at this cat. Instead of seeing all these physical features, all it sees is numbers. And these numbers represent RGB values between 0 and 255. It would actually be a much larger grid for each pixel, but I represented it in an 8x8 grid. So once it has this grid of numbers, it turns it into a matrix, and inside of the neuron, it multiplies it by another matrix of weights. And weights are essentially the internal bias of the computer that basically to focus on the important parts of the image rather than focusing on every pixel. So let's go back to this image. If we were to look at a pixel at the top left, there's really nothing in that area that could tell us that this image is of a cat. So the weights would be relatively low, and it would have a much lower bias, so it doesn't factor in that area. But if we were to look at the facial features, there would be much higher weights, so that there's much more. It gives much more importance to that area to tell us that it is a cat. So once it's multiplied by the weights, we get a weighted sum that's put through an activation function, which I'll get into in a second, and then we get an output that's fed to the next neuron. So inside the activation function, there's an equation that looks like this. This activation function is called swish, and it's the one that's running in my large language model. But there are many other activation functions, such as relu and sigmoid, that all have different use cases. Inside of swish, there's the equations graph something like this, and when the weighted sum is put through the equation, it's plotted somewhere on this graph, and depending on the area, the position on the graph, it determines which neurons to activate in the next layer, and ultimately what the final output should be. So this whole process is really slow, as it's going through every pixel to analyze an entire image. So in 2017, Google researchers invented the vision transformer, which is a much more efficient way to do it. So instead of going through every pixel, the vision transformer splits the image of the cat into patches that are 5 by 5 or 16 by 16 pixels. Now, all simultaneously, these patches go through a linear projection and then are given a positional embedding with it. So now it knows what's inside the patch, and it knows where the patch is. So after going through a transformer encoder, it's able to reconstruct that image all at once, making the whole process much more efficient and faster. So now, specific to my large language model, I use Llama 3.2 Vision. And this is a Vision large language model developed by Meta, and it's now been iterated onto Llama 3.4. But at the time I developed Iris, it was only at 3.2. So Llama works with a three-stage process. There's the vision encoder, language model, and integration layers. And basically, the vision encoder is what I just described, the whole processing of the image. And the language model utilizes any text prompts that could go with the image at the same time. So it's able to use that, like it could be a question or a statement, to target its analysis on the image. And that is done using the integration layers that basically brings the language model and vision encoder together. So this graph shows the performance of Llama versus its competing vision language models. As you can see by the orange and blue lines at the top, Llama is outperforming all of its competitors by a significant margin. And I'll get back to this graph in a second. Because since Llama is so powerful, it has 11 billion parameters and takes up almost 8 gigabytes of storage. So running it for the first time took me 40 seconds to get an output. And since that's obviously way too long for any visually impaired person, I quantized it. And what this means is instead of having every pixel be accurate to a large string of decimals, it's shortened to just 1 or 2, so that it's eliminating unnecessary accuracy. Now I quantized it down to int 4, and as you can see, with 4-bit quantization, we're still retaining almost nearly maximum accuracy. So we're not losing any of the performance of the model. So on top of quantization, to further increase the efficiency, I fine-tuned the model, which essentially means I'm eliminating unnecessary tasks. So Llama, since it's able to do so many things, I can remove stuff like math, or like the ability to do math, so that it doesn't have to do that anymore, and it's reducing the size and improving the performance overall. So the next part of the pipeline was the input and output prompts. At the beginning, there's an audio to text conversion so that we're able to communicate to the algorithm. So I essentially built a 2-stage speech recognition algorithm. The first one is listening for the command word iris, and once it's heard, it activates the second stage, which is now listening for a question or a prompt. At the same time, it's taking a picture of the surrounding scene, and both are fed together into the Vision large language model. After there's an output from the language model, it's converted back to speech using Google text-to-speech and relayed back to the user through audio feedback. So this is what I got when running the model. I first took a picture of my room and asked how could I leave the room. It told me that the door, it was slightly open, the handle was located on the right, and there were obstacles such as the shelf and a wall on my left. Now, using that information, I could clearly reconstruct a general image in my mind that I could use for navigation. And it would be incredibly useful for a visually impaired person because now they understand how to navigate the area and can trust that there are no obstacles in their way. Next, I took a picture outside of my room and asked for the scenery. So instead of actually looking out for danger, I wanted to just create a picture of a scene in my mind. So it gave me more details about each object, such as the color, and so it told me about the gray car and blue car, the basketball hoop, and then the grassy lawns and surrounding neighborhood scenery. On top of that, it also understood that since there was a road, that is a danger to the user. So it warned me of that road. And building off of that, since crosswalks are the most dangerous place for any visually impaired person, I fed an image of a crosswalk and asked if it was safe to cross the road. I was able to understand that since there were no cars at the intersections, the crosswalk was safe. And even if there were to be a car off the screen to the left, since there was a pedestrian crossing at the time, it is still safe to cross the road. So, in conclusion, the white cane, compared to Iris, has a range of 4 meters, while Iris was able to have a range with accuracy over 50 meters. And then for accuracy, while I explained the white cane was only able to detect an object's location or size, Iris was able to accurately depict images with 98.6% accuracy, which I tested using a program called Unsloth AI, and it fed 150,000 images through the algorithm to get this accuracy result. Looks like I have a video of the demo, but because of Wi-Fi problems, I'm not able to show it. But these are some more images, and I basically talked to the algorithm, and it gave me audio responses in less than a second. So in the future, I want to focus on 3 things: portability, self-activation, and 360-degree vision. Right now, because of I was not able to get access to powerful computer chips such as the Qualcomm Snapdragon, which is what Meta uses on their glasses. I was only able to run this algorithm on my stationary GPU. However, the algorithm is efficient enough to run on smaller devices such as NVIDIA Jetsons or the Qualcomm Snapdragons. Next is self-activation. Since every time I'm having to speak to the glasses to get a response, in the future, I would develop it to have a constant awareness and warn me before I would know to ask for something. So that way it's completely independent of me, and it'd be constantly talking to me and giving me warnings or descriptions of a scenery without any assistance. And finally, 360-degree vision. Instead of looking just in front with like a 270-degree view, if I was able to analyze my full surroundings, I would feel much safer and would require even less, I would be like less afraid to go through more dangerous areas. These are all the references I used for this project, and I'd also like to thank my mentor, Dr. Rabail Yasrab from Oxford, for all his assistance. Thank you.